Welcome back, my little orangutans. Today, we're going to talk about the wonderful world of exponential growth and decay. It's going to be exciting. It's going to be riveting. You're going to love every second of it. And if you don't, I'm going to call your mom and tell her that you're being ungrateful. So, let's talk about exponential growth and decay functions. And it's going to be tight. You're going to like it, I promise. All right. So let's first talk about what is the difference between a growth and a decay function. Okay, I'm glad you asked. I didn't ask. Yes, you did. The difference between a growth and a decay function is the base. If the base is a number larger than 1, if b is greater than 1, then it's exponential growth. Let's take a look at that. Let's say we have f of x equals 2 to the power of x. And let's plug in some values of x. How about 1, 2, 3, and 4? Let's figure out what y, or rather f of x is. For 1, 2 to the first power is 2. 2 squared would be 4. 2 to the third power would be 8. And then 2 to the fourth power would be whatever 16 in Italian is. Cool. So do you see how the numbers are growing? They're increasing as we increase x. That's an exponential growth function. If the base of the exponential is between 0 and 1, so it's a decimal or a fraction where the bottom number is bigger than the top number, it'll be an exponential decay function. Let's take a look at one of those. So let's say f of x equals a half. The power of x. If we look at x and we look at f of x, and we'll look at 1, 2, 3, 4. 1/2 to the first power is 1/2. Anything to the first power is itself. 1/2 squared is 1/2 times 1/2. So 1 times 1 is 1. 2 times 2 is 4. It's 1/4. Then times another 1/2 would make this 1/8. And then the fourth power would be 1/16. So these are getting smaller and smaller and smaller. If you want to graph them, so let's say there's 1. So 1 would be a half, then half of that, then half of that, then half of that. They're going to get smaller and smaller and smaller like that. So this is a decay function. So now the next question you should probably ask me is, Mr. Barton, this isn't an or equal to, and these aren't or equal to's. What happens if b equals 1? Well, let's look. If b equals 1, and we plug in x for some f of x's, let's plug in 1, 2, 3, 4. 1 to the first power is 1. 1 squared is 1 times 1, which is 1. 1 to the third power is 1 times 1 times 1, so that's 1. And I'll give you a guess at what 1 to the fourth power is. It's 1. So we don't do 1 because nothing happens. It's boring. It's not... it doesn't do anything, okay? I won't say it's boring because you probably think all of math is boring. You're like, the whole thing's boring, Mr. Barton. But what would you rather do? Would you rather watch a bunch of different bad TikToks or the same bad TikTok the whole time? See, one's less bad than the other. So let's go do some practice. I lied. I got you. You thought we were gonna practice. Just kidding. So let's talk about the formula for growth and decay functions. Yeah, okay, let's talk about this. We'll look at both, I believe. So there is an exponential growth and decay function, and this is used if you know like by how much you're growing. This is more like if instead of like doubling every time or tripling every time, you're growing by like 7% or something like that. then this one is better for percentages and stuff like that. If you're like doubling or tripling or cutting in half, then the one we just looked at is better. So the growth and decay functions is a of t, and this is like function notation. This is f of x, except the name of the function is a, and we're plugging times into it, not just random x variables. So this is a of t, meaning the ending amount is equal to a, which is the initial amount, how much you start with, times 1 plus r. And r is our growth rate. R is positive for growth, or decay rate, and r would be negative. This r should be a decimal, not a percentage. If you plug in the percentage, like let's say they tell you r equals 7%. If you plug that in here, if you plug in 7, it's not going to work. It's going to mess it up. You would have to plug in 7% as a decimal, which is 0.07. Okay. And then t is just the amount of time for whatever thing you're looking at. All right. So when you're simplifying this, what I would do is I would add 1 in r. Then you want to do the exponent next. And then whatever you get when you're done with that, multiply it by a. Remember, we're going to do PEMDAS, which is our order of operation, of course. So you start with the parentheses, then do the exponent, then multiply. And then you don't really have to worry about the rest of that stuff for these types of functions. So now let's look at examples. All right. It says, given the following equation, determine if it is growth or decay and find the initial amount and the rate. All right. So a couple of things that we need to do here. Is it growth or is it decay? So the way we can tell is we look at the base, the number that has the exponent on it. So the thing with the exponent is this. And we said if b is greater than 1, it's growth. And if b is greater than 0 but less than 1, it's decay. So this number, 2.25, is bigger than 1. So this would be an exponential growth equation. Now they want us to find a couple of things. They want us to find the initial amount, a, and they want us to find the rate, r. All right. So a is the number sitting in front of the base with the exponent. So in this case, our initial amount will be this coefficient right here, which is 15. This is the initial amount. Now, this thing inside the parentheses is 1 plus the rate. So what we're going to do is we're going to set the base of the exponential equal to 1 plus r, and then we're going to solve this equation for r. So we just subtract 1. So r, in this case, is 1.25, which is the same thing as 125% growth. Cool. All right. Not too bad. Let's do another one just to make sure you understand. So is it growth or decay? We look at the number inside here, and it is less than 1. So because our base is between 0 and 1, it's a decimal smaller than 1, this would be decay. Our initial amount is the coefficient outside the parentheses. So our initial amount, a, is 1.75. And then to find our rate, we say 1 plus r equals this thing inside the parentheses, 0.75. So now we're going to subtract 1. These cancel. R equals 0.75 minus 1 is negative, because the bigger number is negative, 0.25. So our rate is negative 0.25, which means we're losing 25% of whatever we have every time we do the thing, right? Every year, every hour, whatever the time step is. All right. Let's do a couple of word problems where we actually use the formulas to try and calculate an ending amount, like how much we have after an amount of time. So it says, suppose you deposit $1,500 into an account that pays an annual rate of 6%. No money is added or withdrawn, which is important. You can't take any out or add any more like in between each step, otherwise it's going to get goofed up. Use the formula for exponential growth to write a function for this problem. So what we want to do is we want to take our exponential growth formula, which is a of t equals lowercase a times 1 plus r to the power of t. And all we're going to do is fill in a, r, and t. So this is going to stay the same. Our final amount, a of t, is just going to stay a of t. Our a value, our starting amount, it says you deposit $1,500 into the account. That sounds like how much the account starts with to me. So a, we're going to make 1,500 times 1 plus r. R is our rate, which is 6%, but we can't leave it as a percentage. We need to take 6% and convert it to a decimal. So to do that, we put a decimal after the number because there wasn't one, and then we move it 2 places left. So 1, there's nothing here, so we put a 0, 2. So 6% would be 0.06. So this is going to be 1 plus 0.06, which is 1.06. And then they don't tell us any time, so we leave t as a variable. So this is our equation that will tell us how much money we have after however much time. You just have to tell us how long you want to wait, so we know what number to plug in for t. So that's exactly what they do. They say, how much money will there be in the account after 5 years? So let's plug 5 in for t. So we have a of t, or rather, we could say a of 5. So knowing that we're plugging in 5 equals 1,500 times 1.06 to the power of 5. This is not a multiplied by 5. This is just saying I'm plugging the number 5 into the a function. Don't multiply here. This, we're just going to type into a calculator. So we're going to type exactly what we see. 1,500 times, put parentheses, 1.06, close your parentheses, and then put an exponent of 5 on that and hit enter. And then your calculator will spit out your final amount. So the amount we have after 5 years is equal to, and we're looking at dollars, $2,007 and 33.8, so 34 cents. So that's how much we have. So basically the hard part is coming up with your formula. Then you just plug in t and throw that whole thing in your calculator very carefully. Let's do another one just for practice. So it says you deposit $2,000 into an account that pays an annual rate of 4%. No money is added or withdrawn. So let's write our formula. Our formula is a of t equals a times 1 plus r to the power of t. A is our starting amount. We're putting in $2,000. So a of t equals 2,000 times 1 plus r is 4%, but we need to change 4% into a decimal, so it's 0.04. So 1 plus 0.04 to the power of t. And then they ask us how much money will be in the account after 3 years. So we're going to have a of 3 equals 2,000 times 1.04 to the power of 3. And then we type this whole thing into our calculator. So we do 2,000 times 1.04. I messed up there. 4 to the power of 3 equals, we're going to have $2,249.728. But the 8 tells us to round this up to a 3. Because you can't have 0.8 cents, right? That doesn't exist. There's not parts of a penny. All right. So after 3 years, we gain $249.73, which is nice. That's $249 you didn't have before. All right. Let's look at an exponential decay problem, and we're going to see that they're very, very similar. So we have a population of 1,860,000, and it decreases 1.5% each year. This is probably like some kind of, I don't know, what kind of population decreases each year? Maybe this is like wild coyotes or something, because people hunt coyotes because they're pests and they like kill people's cats and stuff. I don't know. Something. It's some kind of thing that is going away. Or maybe it's a thing we don't want to go away. Maybe it's like orangutans because we're deforesting the Amazon. But, yeah. Anyway, it doesn't matter what it is. Let's write our function. So our equation that we're going to model it on is a of t equals the starting amount times 1 plus r, the power of t. All right. So our starting amount is this population. We're starting with 1,860,000. So we're going to have a of t equals 1,860,000 times 1 plus r. Except because we are decreasing, this is going to be a decay function. So instead of adding r, what we need to do is change this to minus r. So we're going to subtract 1.5% from 1, but we need to change this to a decimal. So changing 1.5% to a decimal, we go 1, put a 0, 2. So it's 0.015. So we're going to do 1 minus that. And we use our calculator and we get 0.9 to, wait, sorry, no we don't. 0.985 to the power of t. All right. Now, what will be the population in 20 years? So now we just plug in 20 for t, and we have a of 20 equals 1,860,000 times 0.985 to the power of 20. And then we type this whole thing into our calculator very carefully. The power of 20. And we get a of 20 equals 1,374,793.7. But we can't have 0.7 orangutans or coyotes. So what we would want to do, because this is a population and we're looking at things that you can't cut up, right? I mean, you can cut up a coyote, but that's kind of gross and morbid. So let's just round to the nearest coyote. So the 7 would tell us to round our 3 up to 4. There we go. That would be your answer. All right. Hopefully this isn't too bad. Really, it's just, can you plug some numbers into a formula? But if you're having trouble with this, please ask for help. Don't just sit there and struggle, or even worse, not do your homework and not try at all. There's nothing worse than people who just quit because they're too scared to try. Cowards. They're just numbers. There's nothing scary about numbers on a piece of paper. You're going to be scared of numbers on a piece of paper? I can't believe you. What would Goku say? Do you think Goku probably is scared of numbers? He's bad at math, isn't he? I don't know. I don't remember the lore. But anyway, if you need help, let me know. Until next time, have a wonderful day.